All right, team, let's talk about kinetic energy and let's explain how mass and velocity affect kinetic energy. Kinetic energy, it's the energy of motion. And when we say motion, think velocity. An object in motion has a velocity and therefore it has kinetic energy. So, simply, if you're moving, you have velocity and you have kinetic energy. Any moving object has kinetic energy. So how does mass affect an object's kinetic energy? So let's think about it. You see a moving object. If that object has more mass, does it then have more energy? A good way to measure how much energy an object has is to see how much work it can do or how much energy it can transfer. So let's run an experiment where we transfer some energy and see if we can notice any changes. So let's transfer energy from this Hot Wheels car to this box by sending this Hot Wheels car with a certain velocity, and it collides with this box and they start to slide because the energy is transferred, and it stops about there. So the car and the box, they have this little sliding distance about that far. So that's how far they went. This distance that the box moved, that's a great indication of how much work or how much energy was transferred. So by seeing that distance, that gives us a good idea for how much kinetic energy that car had. So let me capture these little this car again, and I'll rewrite that distance. So that was trial 1. It went about this far, and that tells us how much energy was transferred or how much work was done. And we'll send this car off again, but this time let's make him a little bigger. We'll make the mass, we'll double its size. We'll make him twice as large. So we've made the mass of the Hot Wheels car. I'm having a hard time grabbing it. Let's try again. Make the mat. Hey, why are you not doing that for me? Boom. There we go. So now he's about twice as big of a car, has twice the mass, and we send him forward and he collides with the box and then he starts sliding. So let's think, physics geniuses, does he slide less far than in trial 1? Does he slide the same distance and therefore the same energy? Or does he slide further? Well, if your intuition was that he slid further, then you are correct. And in fact, he slides twice the distance when the mass doubles. So what does this tell us? This tells us that when we doubled the distance, we doubled his energy. So when we doubled distance, I meant to say double the mass. When we doubled his mass, we doubled his energy. And in this case, it was his kinetic energy because he was moving. So what does that tell us? A doubling and a doubling, that tells us that there is a direct relationship between mass and kinetic energy. So how does velocity affect an object's kinetic energy? So we've seen how mass affects an object's kinetic energy. How does velocity affect an object's kinetic energy? We have this perfectly drawn skateboarder down here. Let's give him some velocity to the right. He's got a certain mass, and in this case, we won't change his mass, but we will change his velocity. Let's check out trial 1. Let's see how high up this blue ramp he gets. When we give him some velocity, he goes forward, and he makes it that high before rolling back to his initial position. So if he made it that high, we should make a little marker there. And that's about how high up he went. He went about 1 meter high up that ramp. Now, a great way to see how much kinetic energy he has is to see how much energy transformation occurs. So he started with a certain amount of kinetic energy, and that energy is transformed into potential energy, and so that energy that we give him is going to determine how high up he gets. So let's double his velocity and see how much more energy he has. So we've doubled his velocity. So we send him forward with that velocity, the doubled velocity, and he goes up, 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 and away. Oh, whoa, I like totally lost. Nope, he's back down there. He goes all the, I'm going to get the ramp. He goes all the way up to 4 meters high. So we have effectively quadrupled his height, which means his potential energy has quadrupled. Which means that if he has twice the energy up here, he must have had not twice. If he had 4 times the energy up here, he must have had 4 times the kinetic energy down at the bottom, which tells us the relationship. So when we doubled velocity, if you double the velocity, we quadruple the kinetic energy. Oh my goodness, folks. That is a new relationship. That is not what we saw there. That's not a direct relationship. This is something called a square relationship. This is a square relationship. Now, a great way to see that is when we write the kinetic energy equation out. So you haven't seen this yet, or at least I haven't shown it to you yet. So let's write down the kinetic energy equation. I'm going to write it down in below. Kinetic energy equals 1/2 times m mass times velocity squared. And what this shows us is that kinetic energy is directly related to the square of the velocity. I'm going to write that one more time and say it out loud, and I want you guys to do this too in your notes. Kinetic energy is directly related to the square of the velocity. So this is a square relationship. Another way so let's write it down in a whole sentence. Kinetic energy is directly related to the square of the velocity. There is a square relationship between kinetic energy and velocity. So what does that mean? What is a square relationship? So how did we change the velocity? We doubled it. We doubled the velocity. And what was the effect on the kinetic energy? The kinetic energy was quadrupled. Now, let me show you guys some other changes that you could have done to the velocity to see what the kinetic energy, what the effect would be on the kinetic energy. If I had tripled the velocity, I would see that the kinetic energy would be multiplied by times 9. If I halved the velocity, if I divided the velocity by 2 or multiplied it by 0.5, if I halved the velocity, we would see that the kinetic energy would quarter or times 1/4. Now, I want you to look at how these changes are similar to one another. Think about 2 and 4, 3 and 9, 1/2 and 1/4. They are squares of each other. So if I take the number 2 and I square it, that is the same as multiplying it by itself, and that 2 times 2 equals 4. If the velocity changed by a factor of times 3, well, 3 squared is the same as 3 times itself, which is 9. If I have a half, that's the same as a half. If the velocity changed by a factor of a half, if the velocity was divided by 2 or was multiplied by 0.5, then the factor that I got lost in my words just now. So if the velocity changes by a factor of 1/2, 1/2 squared is the same as 1/2 times 1/2, which equals 1/4. So notice how a square relationship, and we'll get into the definition in just a second, is if one variable changes by a factor, the other variable changes by that factor squared. So that's what a square relationship shows us. Let's look at it on a graph. Let's look at it on a graph real quick. So what pattern does a square relationship make on a graph? Let me just pause this video now, and I'll just make two parts. That way it'll divide it up a little bit easier. But part one of this video, I want you to just be thinking about how, if an object has kinetic energy, that means it's moving, and vice versa. Mass and kinetic energy have a direct relationship, and then velocity and kinetic energy have this thing called a square relationship. And actually, before we do part two, let's just write down what a square relationship is. I'm going to make a text box here. Let me make the text box a little bit larger. There we go. Instead of doing a text box, I'll just write it. So, a square relationship, if one variable changes by a factor, the other variable changes by that factor squared. Okay? So a factor is a multiplier, or if something changes by a factor, that means that variable is being multiplied by a number. Okay? So that's the definition of a square.